Dear students, today we will learn atoms. In these atoms, we have two parts, that is Thomson's atomic model, Rutherford's scattering experiment, and Bohr's model and a line spectrum. These are the topics, and for competitive examinations they are asking questions from Rutherford's scattering experiment. So let us see Rutherford's scattering experiment. See, this is the experimental setup diagram of Rutherford scattering experiment. See here, this is a lead block and it contains source of alpha particle, and this is a slit, and this is a thin gold foil, and this is a microscope to receive scattered alpha particles. And here, by varying this theta, this is called scattering angle. By varying this theta value, they have observed number of alpha particles scattered in different directions. With this data, they have plotted a graph. This is the graph. Here on y-axis, they have taken number of alpha particles scattered at a theta angle, and here on x-axis they have taken theta in degrees. See, this is one rectangular hyperbola. From this we can understand most of the alpha particles have scattered at a smaller theta values, and a very few number of alpha particles are scattered with a large theta value. From this experimental observation, from this they have come to the conclusion that atom is having most of the space empty. Most of the space in atom is empty, and there is positive charge concentrated at the center of the atom. See this. See, this is the conclusions. These are the conclusions they got from alpha particle scattering experiment. See here, this is the atom, suppose that, and entire positive charge and entire mass of the atom is concentrated at its center, and most of the space is empty. That's why alpha particles are scattered less. Most of the alpha particles have passed through this empty space, and very few, 1 in 8,000 alpha particles are scattered with 180 degrees. And electrons are revolving around this nucleus in circular orbits. So these are the experimental conclusions from Rutherford experiment, and here we can get an expression for distance of closest approach. See this. Suppose this is the nucleus and alpha particle is moving with velocity v. It approaches the nucleus up to certain distance. Because of repulsion, it will deviate its path. So here r is the distance of closest approach. R is a distance of closest approach. And here this distance of closest approach can be calculated by applying law of conservation of energy. That is, here kinetic energy of alpha particle gets converted into potential energy. That's why we can write half mv square is equal to 1 by 4 pi epsilon naught into ZE into 2E divided by R. From this we will get the expression for closest distance of approach of the alpha particle, and this closest distance of approach is approximately taken as radius of the atom. And here they have developed a relationship between impact parameter and a scattering angle. See, this is the nucleus. Suppose alpha particle is approaching nucleus like this, and here at this position it scatters. This is scattering angle. This perpendicular distance is called impact parameter, and this is the relationship between impact parameter and scattering angle. From this relation, what we can understand? See, for a given impact parameter, if kinetic energy of alpha particle is increased, then what happens? This is increased and here this is constant, so this must increase because this ratio must be a constant. As cot of theta by 2 increases, theta value decreases. That means most energetic alpha particles are scattered with less deviation. And here you see, if a B value decreases for a given alpha particle of having some kinetic energy half mv square, for a given alpha particle, if a B decreases, if this gap decreases, then what happens? Then cot theta by 2 also decreases. As cot theta by 2 decreases, theta value increases. That means for the particles, for alpha particles having less B impact parameter, they will have more scattering angle. That means alpha particles coming with a smaller impact parameter, something like this, these alpha particles will scatter more, whereas these alpha particles, you see, for these alpha particles impact parameter is a little bit more. That's why they scatter with a less scattering angle, they will deviate with a less scattering angle. So these are the results of Rutherford experiment. Now let us see some problems based on these results. Now come to this first problem. See here what is given is an alpha particle of energy 5 MeV is scattered through 180 degrees by a fixed uranium nucleus. The distance of closest approach is of the order of. See here they are asking, they are given kinetic energy of alpha particle. Kinetic energy of alpha particle, that is half mv square, is 5 MeV. That is, we have to convert into joules. So when we convert it into joules, we will get this value. And these are scattered through 180 degrees by a fixed uranium nucleus. Suppose this is the uranium nucleus. For uranium, Z value is 92. Suppose this is the alpha particle, and this alpha particle scatters through 180 degrees. See here, R is the closest distance of approach. So here we can write, when the particle approaches the nucleus, here in this case we can write, at this position kinetic energy of alpha particle is equal to potential energy between the nucleus and alpha particle. So here we can write half mv square is equal to 1 by 4 pi epsilon naught into 2 ze square divided by r. From this we can get r is equal to 1 by 4 pi epsilon naught into 2 ze square divided by half mv square. Now substitute the values. You know 1 by 4 pi epsilon naught value is 9 into 10 power 9 into 2. Z for uranium is 92 and E value 1.6 into 10 power minus 19 whole square divided by half mv square. This half mv square value 5 into 10 power 6 into 1.6 into 10 power minus 19. This value is roughly 2.3 into 10 power minus 14 meters. So this is the result. Okay. Now let us see one more problem. See this problem. This is the second problem. Here what they have given is calculate the impact parameter of a 5 MeV alpha particle scattered by 90 degrees when it approaches a gold nucleus. For gold, you know, Z is equal to 79. So here, you know this formula. Impact parameter B is equal to 1 by 4 pi epsilon naught into ZE square into cot of theta by 2 divided by half mv square. Now substitute the values. 1 by 4 pi epsilon naught value 9 into 10 power 9 Z value 79, E square, that is 1.6 into 10 power minus 19 whole square, into cot of theta is 90, so it is 90 by 2, divided by half mv square, kinetic energy of alpha particle in mega electron volts. So we have to convert it into joules. So we can get 5 into 10 power 6 into 1.6 into 10 power minus 19. So if we calculate this, we can get 2.7 into 10 power minus 14. So this is problem number 2. Now we see one more problem. Now come to this problem. See here what they have given is the number of alpha particles scattered at a 60 degree is 100 per minute in an alpha particle scattering experiment using gold foil. Calculate the number of alpha particles per minute scattered at 90 degrees angle. So here they are given scattering alpha particles at two different angles. Here you see this is the relation. See, this is the relation between number of scattered particles and scattering angle theta. Here in the question they are given, from this we can write n1 by n2 is equal to sine of theta 2 divided by theta 2 divided by 2 divided by sine power 4 of theta 1 by theta 2. Now you substitute n1 value is 100, n2 value they are asking, so it is sine power 4 of theta 2 is 90 divided by sine power 4 of theta 1. Theta 1 is 60 divided by 2. So here what we can write is, that is 1 by root 2, sine of 90 by 2 is sine 45, that is 1 by root 2, again power 4 is there, divided by sine of 60 by 2, that is sine 30 is 1 by 2, power 4. So it is this is 1 by 4 divided by 1 by 16, that is 4. From this we can find n2 value. n2 is equal to 100 divided by 4, that is 25 per minute. So this is the third problem. Now we can see one more problem. See, this is fourth problem. In Rutherford's scattering experiment, when a projectile of charge Z1 and mass m1 approaches a target nucleus of charge Z2 and mass m2, the distance of closest approach is r0. The energy of the projectile is, see here, in this question they are asking energy of projectile at closest distance of approach r0. Kinetic energy of alpha particle is equal to potential energy, that is 1 by 4 pi epsilon naught into q1 q2 divided by r, that is equal to 1 by 4 pi epsilon naught into q1, that is alpha particle charge, that is 2e, and q2, that is projectile charge is z1 into e, into nucleus charge, that is z2 into e, divided by r naught. Now from this we can get kinetic energy of projectile k is directly proportional to z1 and z2. So the option is first one. So these are the problems based on Rutherford scattering experiment. So in next slide we will go to Bohr's atomic model. Thank you.